Okay, a nice application of the ideas we've been talking about is in a problem called the hat matching problem. This is a great example or application of the Poisson approximation theorem. So what is the hat matching problem? So we're assuming that there's n people and n hats. So each person has a hat. And what happens is the idea is, okay, n people and n hats, and um, everybody throws their hat into a box, let's say, and every person is going to leave the restaurant and they're going to pick a hat at random out of the box and they're going to leave. And so the question is, how many people are going to pick up their own hat? And so most likely, so there's a chance that everybody picks up the wrong hat. How many people are actually going to get the right hat? So we choose. Okay, so with that description, let's let A sub in be the event that the ith person picks his own hat. And so n sub n becomes in the above. So this is in the framework of the general Poisson approximation theorem. N sub n is the number of people who pick their own hat, who pick the correct hat. Then what can we say? So up above, we have the double star, right? Double star is here. This holds. Double star holds if. So for each n, the AINs are exchangeable. As n goes to infinity, the probability of any given event goes to 0, such that the expectation of n sub n, which is equal to n times the probability of A times 1n because of the exchangeability, is equal to some fixed value lambda. And the AIs are asymptotically independent in the sense that if you were to consider the probability of the intersection, how does that behave relative to the product of the probabilities? Then that converges to, so that converges to 1 for all fixed. Okay. Then in this case, the value of SKN, which is n choose k, probability of A1 intersect AK, well, we can write n choose k as is 1 over k factorial n fall k over n to the k times n probability of a1n to the k times probability of the intersection over the product, which we've assumed is approximately 1, right? So this is approximately 1. This is lambda to the k. This is approximately 1. And this is 1 over k factorial. So this is going to lambda to the k over k factorial. And so for a hat matching problem, we do have exchangeability. We do have that n times the probability of a1n. What's the probability of a1n? It's the probability that somebody picks their hat. Well, by exchangeability, the probability the first person who picks their hat is 1 over n, because there's n hats in there and only 1 is the right hat. So it's n times 1 over n, which is 1. So we expect one person to get the right hat. And the probability of any k-tuple of these events happening, that is 1 over n fall k. And the product of the probabilities of each of them happening, we already know, is 1 over n to the power k. Because it's 1 over n for each, which does converge to 1 as n goes to infinity. Therefore, we can use the Poisson to approximate the number of people who pick the right hat, which would be approximately Poisson with parameter 1.